In this video, we're going to discuss one particular type of reaction, the acid-base reaction. Really, acid-base reaction is a combination reaction. It involves an H plus and an OH minus forming water. However, acid-base reactions are ubiquitous in any aqueous environment because water naturally can go backwards. Two waters can slam into each other, and then you can have it break apart where you get a hydroxide and an H plus. There's always a little bit of H plus and OH minus in any aqueous container. As a result, any reactions that these can do show up in every aqueous environment that we can look at, and biological systems especially utilize this immensely. However, we also utilize this a great deal in just general chemistry. We need to reference a few terms here. Strong acid, or strong base, versus weak acid, or weak base. This is not referring to how dangerous an acid or base is, but rather it's a technical term that means whether it fully dissociates or not. So a strong acid or base 100% separates, where a weak acid and base is less than 100% separation. Examples of this type of thing, well, what is it to be an acid or what is it to be a base? And therefore, what is it to be a strong acid or a weak acid or a strong base or a weak base? Our acids are any molecule that will release H+. So an HCl gas, when it's put into water, becomes H plus aqueous and Cl minus aqueous. And HCl is a strong acid. It 100% breaks apart. So if you put 1 mole of HCl gas into a liter of water, you will get 1 mole of H plus floating around and 1 mole of Cl minus floating around. This is the idea of an acid. Acid releases H plus. Well, our weak acid is just less than 100%. So this would be something like ammonium. NH4 plus will break apart in water to form H plus and NH3, which means that our ammonium was an acid. It gave away H plus. And so we had acid, They broke apart to give away H plus, but ammonium does this a tiny fraction. 99.99% is still ammonium. Only a little bit succeeds at breaking apart into H plus and ammonia. Well, our base, there are two general ways we think about base at this point. One is releases OH minus or consumes H plus. The OH minus consumes H plus. So some materials release OH minus and let that do the consuming. This would be things like sodium hydroxide. Sodium hydroxide breaks into a sodium and an OH minus, and that OH minus will absolutely react with H plus to form water. So we consider sodium hydroxide a base. Really, it's the hydroxide that gets freed up, but we consider the source to be the base. However, well, I can have things like NH3. NH3, if it runs into an H plus, will stick together and make NH4 plus. In fact, you may have noticed a little bit here, there was a double-headed arrow. This is an equilibrium. It goes back and forth. Your weak acid will break apart, but the things it breaks into can recombine. Ammonia, NH3, is a base because it can consume the H+. It can react with that H+, they'll just stick together. And what does it look like when they've stuck together? It looks like NH4+, because that's what it is. It's 4 hydrogens, a nitrogen, and a positive charge. Our weak acid actually had its base as one of the products. And our weak base actually has its acid as one of the products. These are a pair. Your weak acid and its conjugate base are a conjugate pair. They innately have to be together because whenever the weak acid falls apart and does its job of being an acid, well, there's something left afterwards. Whatever that thing is, in this case NH3, that is a base. It can react as a base, react with H+, and go back to being that original acid. Our strong acid and base don't have this. Chloride is not a base. Sodium is not an acid. Strong acid and bases don't have this complication, where weak acids and bases do. This is why we need to have different terms for them. There's differences in behaviors as a result. Weak acids and bases would need to be calculated out using equilibrium, which is something that will happen later on in calculations in 162. But strong acid and bases can be calculated using just standard stoichiometry. So a lot of times our reactions with acids and bases involve using strong acid and base to react with each other. If I have a beaker and it has some H+ in it from some source, and I want to know how much, how concentrated is that acid? What is its molarity? Well, I could pour out a little bit of it, let's say 100 milliliters. I could put that 100 milliliters under a device where I could add a base, say sodium hydroxide. Well, there's some amount of H+ down here, and drop by drop, I would add the sodium hydroxide. And every time it fell in, I'd get a sodium hydroxide, it would react with an H+, another sodium hydroxide and react with the H+. As I add drops, eventually my H+ would get used up. We can actually observe this. Special molecules called indicators will change colors depending on if there's H+ around or not. And so phenolphthalein is a common one. It turns pink once all the H+ is gone. And so suddenly as I add just a little bit extra hydroxide, the solution turns pink. Well, if I know what the hydroxide was, if I knew it was 0.1 molar NaOH, and I watched what volume I added. I started here, it went down, and I got to here. I could measure that and say, oh, that was 12 milliliters. Or whatever the volume we actually had to add was. In doing so, I could know the amount of sodium hydroxide I had to add, and it's 1-to-1 with H+. So if I know what sodium hydroxide I had to add until all the H+ went away, because it turned pink, then I can figure out how much H+ was there. As long as I don't add too much extra sodium hydroxide. This is why we do it drop by drop. A method called titration that we'll discuss more in another video. But this is a way that we can actually test how much acid was in an unknown solution. And this is common for runoffs from mining industries and the like. Any process that produces a lot of acid, need to know how much acid there is. Do we need to process it? Can we dilute it? Can we react it with sodium bicarbonate and quench it? Like, what exactly do we need to do? How acidic and how dangerous is that solution we've created? This is a method by which we can do that. And so acid-base reactions are pretty common. They're also useful for tracking how much product has been made. If a base or an acid is produced in a reaction, well, we can figure out how much reaction occurred by figuring out how much acid or base was made. There are plenty of balanced reactions where H+ or H- is one of the products. This is the idea in general of an acid and base reaction. There's strong acids and bases, there's weak acids and bases. We're only really going to focus on strong acids and bases in our calculations for now, and they can just be done, treated like stoichiometry. Our calculations for them behave exactly the same as any other amounts that might have in solution. Example here, that's sodium hydroxide. If I have 12 milliliters, it's 0.012 liters of the NaOH solution. I was told that it was 0.1 molar, so in every 1 liter of the NaOH solution, there's 0.1 mole of sodium hydroxide. And so we can calculate out just how much sodium hydroxide we added, 0.0012 mole of NaOH. Well, if we assume in our balanced reaction that NaOH, and let's say we thought it was HCl. So there's some amount of HCl, we didn't know how much, in our original container. Well, is it going to react? You're going to get water, and you're going to get sodium chloride. The OH minus, the H plus will react to make water. That leaves sodium and chloride to pair together. This is 1-to-1, so I must have just as many 0.0012 mole of HCl. Well, that HCl was in the 100 milliliters, which means I know the moles and the volume. 0.0012 mole of HCl over 0.1 liters means there was 0.012 molar HCl. What was that original unknown concentration? It's 0.012 molar, or 12 millimolar. Provided that HCl had been produced by some other reaction, we could then use another balanced reaction to figure out how much of the other material we had made. Strong acids and bases, they're a type of reaction, but in the end, it's still just a balanced reaction that we can calculate using our concentrations like any other molarity solution calculation. Weak acids and bases, on the other hand, cannot be done this way. So we'll focus on strong acids and bases for now, and later on when we reach equilibriums, in later courses, we'll dive into weak acids and bases.